Hello everybody, in this lecture we will be solving 2017 IMO problem number 2. Here is a view of this problem. We are given the following functional equation and we would like to find all functions that satisfy this functional equation. It's easy to see that the following functions, f of x equals 0, or f of x equals 1 minus x, and f of x equals x minus 1, all these functions satisfy the given functional equation. So for example, if obviously 0 is quite clear that it satisfies. For instance, let's try this one, f of x equals 1 minus x. So if we plug it in onto the left hand side, let's see if we can come up with the right hand side. So we would have f of so replacing it, so it would be 1 minus x times 1 minus y plus f of x plus y would simply be 1 minus x plus y. And let's work this out. So f of 1 minus x times 1 minus y, again applying the definition of the function one more time, 1 minus x, 1 minus y, plus 1 minus x minus y, and now expanding it, 1 minus 1 plus minus xy minus x, or plus x plus y, I guess, right? So plus x plus y, yeah, plus 1 minus x minus 1. Finally, cancelling similar expressions. So we find out that we get an expression which is 1 minus x times y. But this is simply looking at our function f. That's simply f of xy, right? So does that make sense? So as a result, all these expressions, all these three suggestions actually should work. In fact, one can also observe immediately that if f is a solution, for instance, you can make it into a claim, then it's also the case that minus f is also a solution. Obviously, because you will have a minus plus here, so you will come up with a minus here, and then this one will come out as a minus, and then this one will come out as a minus. So therefore, you can just move the expressions on the right hand side to the left, and those in the left hand side to the right hand side. But anyhow, so we have those three candidates, and we claim that's it. There's no other solution. That's what we need to prove. So like in any other functional equation problem, it's we can start by trying to plug in different values for x and y, especially what happens to the function at the values of f of say 0, right, or 1 plus or minus 1. Those are interesting, and especially what are the roots of our function. So let's start by exploring potential values for f of 0 first. I would like to contemplate what happens if f of 0 is in fact equal to 0. If that was the case, then one can for instance substitute x, and instead of y we can simply substitute 0. So in our expression, so if you start with our functional equation, we will get f of x times f of well, y is replaced by a 0, right? So 0 plus f of x plus 0 equals f of x times 0, and that simply gives us, so f of 0 is 0 by our assumption. Let's say assume, and so this thing is 0, implying this whole thing is 0, implying this whole thing is 0, plus we have f of x here, and that's simply equal to f of 0, but f of 0 is 0. So therefore, we have found that f of x equals 0 for all x is one of the solutions, especially so when if f of 0 is in fact equal to 0. So for the rest of the discussion, I will assume that f of 0 is actually not equal to 0. For the rest of the discussion, that's what we're going to assume. But then, if you plug in x equals 0 and y equals 0 this time in our functional equation, we would get that f of 0 times f of 0 plus f of 0 plus 0 is equal to f of 0 times 0. Now this would simply imply that f of 0 times f of 0, knowing that f of 0 is not equal to 0, is simply f of 0 squared plus f of 0 is equal to f of 0. These two will cancel out, implying that f of 0 squared is simply equal to 0. That's an important result, so let's make note of this. And so that it doesn't confuse with our previous finding, let me highlight the solution. Okay, good. All right. So next, let's find the roots of this expression. So I claim that 1 is a root. So right. So I claim that f of 1 is in fact equal to 0. So let's yeah, so let's try to figure this. Suppose that f of 1 is not 0, right? So therefore, let's say that there's another number, f of c is equal to 0, where c is not equal to 1. So in that case, you can plug in our expression for x, you can plug in c over c minus 1, knowing that c is not equal to 1. And for y, we can simply plug in c. When you plug in these values, we get f of c over c minus 1 times f of c plus f of c over c minus 1 plus c, replace x and y with these two, is equal to f of c over c minus 1 times c. Recall, all I did is to plug in these values in our original functional equation. So that would lead to so there's not much going on in the first expression, but when you look at the second term here, we would get f of, if you find the common denominator, c minus 1 here, and the numerator would be c plus c squared minus c. These would cancel out. That would simply be equal to f of c squared over c minus 1. Obviously, these two terms are just equivalent. They would just cancel out, leaving just the first expression just being equal to 0 as a result, right? So that's, let's just write that down. So that just have to be equal to 0. But recall that f of c was just 0, right? So that was just a 0. So that would finally lead to 0 times something is of course 0. That would lead to f of 0 equals to 0, which is obviously a contradiction. So that establishes that we assumed, we started with something to the contrary, and then we found out a contradiction. So therefore our claim is established, and f of 1 is in fact equal to 0. Now if you combine this result with the previous result, that would immediately imply that f of 0 squared is in fact equal to 1, further implying that f of 0 is equal to plus or minus 1. So for the rest of the problem, let's do a case work. Let's start with f of 0 equals to minus 1, and then it's quite easily you can replicate it, and you can find the same for f of 0 equals 1 as well. So case 1, f of 0 equals minus 1. We simply plug in our expression x and replace y with a 1. That would give us f of x times f of 1 plus f of x plus 1, which is equal to f of x times 1. And from here, that would simply imply, knowing that f of 1 is simply equal to 0, this whole thing is 0. And so we have f of 0 plus f of x plus 1 is equal to f of x. Now, as we said at the beginning, we are in the case where f of 0 is equal to negative 1. So this would further imply that minus 1 plus f of x plus 1 is equal to f of x. Or after organizing this, we get f of x plus 1 equals f of x plus 1. In fact, you can also use an inductive argument. By induction, you can show that f of x plus n is in fact equal to f of x plus n, and I leave this to you as an exercise. Now let's go back to a more important result. So I claim at this point that our function f is one-to-one, or it is an injection. Let's prove this first. As usual, let's have a look at what happens if f of a is equal to f of b. Obviously, because of this result that we have just found, this would imply that f of a plus n is equal to f of b plus n, which is equivalently f of a plus n equals f of b plus n. And now I would like you to consider the following polynomial, quadratic I should say, quadratic x squared minus a plus n x plus b plus n minus 1. Okay, so if you look at this expression and if you are investigating its roots, it's a good idea to start with the discriminant and to ensure that the discriminant is greater than 0. So if I choose a convenient n, which would make that discriminant strictly greater than 0, sorry for that, so this greater than 0, then that implies that we would have two real roots, right? So for a large n, that would hold, right? Because the quadratics would grow faster than a linear function. So therefore there exists, so this should imply that there exists real numbers r and s, which are the roots of this quadratic. So roots such that now if you apply Vieta formulas to our quadratic here, it would tell us that the sum of the two roots, r plus s, is simply equal to minus a plus n, so which is just a plus n. And similarly, the product is simply equal to b plus n minus 1. At this stage, let's go back to our functional equation and plug in this time. Plug in x equals r and y equals s in our functional equation. That would simply give us f of r, f of s, plus f of r plus s equals f of r times s. And this implies that, so let's just keep the first expression intact, plus r plus s. Now r plus s is just a plus n, and this one r times s is just f of b plus n minus 1. Now as again the first expression is just there, so let's just put a dido sign, and this one by the induction thing that we got earlier, like this one, that's simply equal to f of a plus n, and this one on the right hand side is just f of b plus n minus 1. Now we can cancel out n's, and we can as well cancel out f of a and f of b, because that was the beginning assumption here. So we would finally get f of this expression inside is equal to minus 1. Recall that yes, so we are in the case f of 0 is equal to minus 1. So that would imply that the expression inside is actually equal to 0. So that it would imply f of r times f of s is actually equal to 0, or implying either f of r is equal to 0 or f of s is equal to 0. And going further up, we recall that f of 1, it is the root of the function is 1, so that suggests that, implying that either r is equal to 1 or s is equal to 1. Now in either situation, this would imply that, let's assume without loss of generality that r is equal to 1, then it would mean 1 plus s is equal to a plus n, and 1 times s is equal to, using these two, b plus n minus 1. From this, that would imply, for instance, substituting the s here on the left hand side, so this expression, plugging it in, so 1 plus b plus n minus 1 equals a plus n. The n's cancel out, the plus 1 and minus 1 implying that a is equal to b as we desire. So that actually proves that our function now is an injection, is one-on-one. And we have one more step left to establish the desired result. So all I will do is I will plug in simply x, and instead of y, plug in minus x in our function. So we would get f of x times f of minus x plus f of x minus x equals f of x times minus x. And that would simply imply that f of f of x, f of minus x plus f of 0 is equal to f of minus x squared. But recall, f of 0 is simply, we are in the case f of 0 is equal to minus 1. So therefore, this implies that, for example, let's just write it here. So we have f of, let's do it a few more steps before we finish, is equal to f of minus x squared. But then I can make use of the following trick, plus 1 and then minus 1. But then the minus 1 would come out because of our, again, the step where we proved up here, the induction thing. So so that's nice. So therefore the minus 1's cancel out. But then, because our function f is an injection now, if their values are equal, their images, it must be that the values in the domain are equal. So that would imply that f of x times f of minus x is simply equal to minus x squared plus 1. Now I will further plug in now. Let's plug in this time x. For the x, let's just keep the x. But for the y, let's just plug in 1 minus x. Let's see what happens now, and let's see if we can combine it with this earlier result to get something meaningful going. So 1 minus x plus f of x plus 1 minus x equals f of x times 1 minus x. And that would imply, so here we have f of 1, right? The x's cancel. F of 1 was 0 as we agreed, so that whole thing vanishes. Now we have f of the left hand side is equal to f of the right hand side. We can get rid of the f's, because if the images are equal, then the values from the domain must be equal. F of x times f of 1 minus x is equal to x times 1 minus x. Now I will make use of this trick one final time, this one basically. So I can further split this one into two parts. F of x times 1 plus f of minus x is equal to x minus x squared. Now multiplying f of x across this, so we get f of x times f of minus x is equal to x minus x squared. And now boom, so we have already found an expression for f of x times f of x minus x, and that's just minus x squared plus 1 plus f of x, so I don't need the plus sign here obviously, which is equal to x minus x squared. We can simply cancel out the minus x squares, giving us finally the desired result of f of x equals x minus 1. So that's a second solution to the problem. Finally, if you recall, very early on at the beginning of the problem, I suggested that if f is a solution, then so is minus f as well, quite easily shown. So that would suggest that now that we know x minus 1 is a solution, that also implies that f of x equals 1 minus x is also a solution to the problem. If you don't want to do that, then you can go back to the second case. So we have found the case where f of 0 is equal to -1. In the other case where f of 0 is actually equal to +1, right? So remember where we got these things. So that's the one that will be associated with it. So this one will be associated with f of 0 is equal to +1. This solution is associated with f of 0 equals to -1. But therefore we have just established all three solutions. In the case where f of 0 is equal to 0, we have found the first solution as f being identical to the constant function 0, and then in the case where f of 0 is simply not equal to 0, we have found two other solutions, namely f of x equals x minus 1 and f of x equals 1 minus x. And that solves the problem. Hope you enjoyed it and looking forward to see you guys in our next lecture.